Okay, so section 5.2. All right, in order to be successful at multiplying polynomials together, we have to recall an important property of exponents. And that property instructs us to know what to do with exponents when we multiply like bases together. So when we multiply like bases together, we keep the base the same, and we are to add the exponents. We need to know this property if we're going to be successful in multiplying polynomials together. Okay, all right, so let's just begin here. Let's just start looking at some products of polynomials. Suppose I want to take this monomial 4x cubed, and I want to multiply it into this trinomial here. I'm going to try to multiply this monomial by this trinomial. To do that, we're going to have to use our distributive property that we used with real numbers. So this 4x cubed is going to have to get multiplied by the 5x squared. And I'm going to show this intermediate step. When you get better at this, you can omit this step that I'm showing right now. Plus, and then 4x cubed gets multiplied by, we should view this as a minus 3x. Okay, so 4x cubed multiplied by negative 3x. Plus 4x cubed gets multiplied by a positive 1. And this is what we have to take care of now. All right. So when I multiply a 4x cubed by a 5x squared, what am I going to get? Well, 4 times 5 is going to give me 20. So I'm going to have 20. And then I got x to the third power multiplied by x to the second power. And when I multiply like bases, I keep the base the same and I add the exponents. So 3 plus 2 power will give me the 5th power there. Now I want to take 4x to the third power multiplied by negative 3x to the first power. And 4 times a negative 3, as we multiply the coefficients together, 4 times negative 3 is a minus 12. And then x to the third power multiplied by x to the first power is going to be x raised to the 3 plus 1 power, or x to the 4th power. And then 4x cubed times 1 at the end is plus 4x cubed. And this would be our product after having multiplied that monomial by that trinomial there. Does that make sense what just happened there? Okay. So we utilize our distributive property to take care of that product there. All right, we can try another one like that. Now the instructions here will say simplify, or the instructions could say multiply. I'm going to try to take 5a squared b cubed, and I'm going to try to multiply it by this trinomial 8a squared minus 2ab plus b squared. And to do this, we're going to utilize the same technique that we did on the previous problem. We're going to have to use our distributive property here. Okay? So this 5a squared b cubed is going to have to get multiplied by 8a squared. And this is like a optional step, especially when you get better at this. You can omit this step here and the one I'm writing here. I always put plus signs in between my products. Notice that, okay, to remain consistent. Now the 5a squared b cubed is going to get multiplied by the negative 2ab. I will view this as a negative 2ab for the purposes of this multiplication here, so we don't mess the sign up here. Plus, and then the 5a squared b cubed gets multiplied by the b squared way at the end. Okay. This is what we have to do here. All right, now 5a squared b cubed times 8a squared. We multiply the coefficients together, so 5 times 8 nets us 40. And then a squared multiplied by this like base of a here, a squared multiplied by a squared we keep the base a the same, and we add the exponents. So a to the second power times a to the second power is a to the 2 plus 2 power, or a to the fourth power. Now we have a b cubed here that has nothing else to be multiplied by, so you still have to bring this factor of b cubed along. Do not lose it. All right. Any questions how we multiplied 5a squared b cubed by 8a squared and got this? Right there. All right, 5a squared b cubed multiplied by negative 2ab. We multiply the coefficients together first. 5 times a negative 2 gives us a minus 10. I got a to the second power that has to be multiplied by a to the first power. And a to the second power multiplied by a to the first power is going to be a to the 2 plus 1 power, or a to the third power. Finally, I have b to the third power that must get multiplied by b to the first power. And b to the third power multiplied by b to the first power is b to the 3 plus 1 power, or b to the fourth power. And we got that. Finally, we have to multiply 5a squared b cubed by b squared. Well, the 5, technically there's like a factor of 1 in front of b squared here. So 5 times 1 keeps this as a plus 5. A squared has no other like base of a to be multiplied by, but so we just bring the a squared along. And then b to the third power multiplied by b to the second power is going to be b to the 3 plus 2 power, or b to the fifth power. And we are done. This would be the product of this monomial and this trinomial. Is this making sense how we're multiplying a monomial by a polynomial in general here? All right. Okay. And like I said, this meeting is being recorded so that you will, in your, at your leisure, if you missed anything, you'll be able to go back over this to your mathematical heart is content. Okay. All right. So that's multiplying a monomial and a polynomial together. Let's take a look now at how to multiply two binomials together. So if I want to take x plus 4 and multiply this binomial by another binomial, x plus 6, our job is to multiply these together. So I'm going to multiply these together. Now, there's many ways to show how to multiply binomials together. The most orthodox way that usually is illustrated in just about every algebra book you ever look at is called the FOIL method. And this word FOIL is an acronym that enables us to remember how to multiply binomials together. Okay. Basically, the letter F in the word FOIL means we multiply the first terms together. So that means I'm going to multiply the first terms of my binomials together. So this x here will have to be multiplied by this first term of x here. I like to use arrows as a visual cue. You've probably been noticing that. I think that's a very wise thing to do. So we're going to take x times x. So x times x is going to be the product of the first terms of our binomial, plus O in the word FOIL represents the word outer. We need to multiply our outer terms of our binomials together. That would be the terms that are furthest away from each other. That means I got to multiply the x by the 6 over here. So x gets multiplied next by 6. Okay. So plus, now x times 6, it's awkward to say x6, so we will spin it around and call it 6x. This represents the product of the outer terms. Plus, the letter I in the word FOIL represents the product of the inner terms. Those are the terms that are closest to each other. Notice we've exhausted all the products with our first term x of the first binomial. We multiplied it by both terms of the second binomial. So we're done with this x. We move to the positive 4 now. The positive 4 now will be multiplied by the x next. So 4 times x, 4x. That represents the product of the inner terms of the binomial. Inner terms. And then last, literally, the letter L represents the last terms of the binomials that have to be multiplied together. That means we got to multiply the 4, the last term of the first binomial, by the 6, which is the last term of the second binomial, plus 4 times 6. That's the product of the last terms. And you get this acronym FOIL here, okay? FOIL is a shortcut for way of saying we multiply the first terms together, the outer terms, the inner terms, the last terms. That's the algorithm that is normally pushed in all algebra books to multiply binomials together. It's not the only way to multiply these things together, but it is probably the most typical way that is illustrated. All right, here we go. To clean this up. What's x to the first power times x to the first power? When I multiply like bases, I keep the base the same and I add the exponents. 1 plus 1 is 2. So x times x is x squared. Now, here we have plus 6x plus 4x. And at the end, our product is going to be 4 times 6, which gives us 24, plus 24. Notice these two middle terms are like terms or similar terms. They need to be combined. 2 days ago, we seen that in order to add like terms together, we keep the variable part the same and we just add their coefficients. 6x plus 4x is going to be 6 plus 4, or 10 of these x's, plus 10 of these x's. And ladies and gentlemen, we are done. That would be your product of these two binomials up here. And notice our answer, our product is written in descending order. Second degree term, first degree term, and 0 degree term. Any questions how I multiply those binomials together? All right. In all honesty, being intermediate algebra, you probably should have done this somewhere in your past, either in high school or in elementary algebra. I know if you come through elementary algebra here at Mott, you do multiply binomials together quite a bit in there. Okay. So this, hopefully is review. If not, I think I went over it thoroughly enough to show you what's going on here. All right. And we can try another one here. So the instructions might say multiply or simplify. And we will try 3x squared minus 4. And we're going to try to multiply this by 2x squared minus 5. So we're going to try to multiply these two binomials together here. All right, to do so, we're going to use our FOIL algorithm again. So I'm going to multiply my first terms together. 3x squared will get multiplied by 2x squared. Plus, I'm going to multiply my outer terms together. 3x squared gets multiplied by a negative 5. 3x squared times a negative 5. Plus, multiply the inner terms together. Negative 4 multiplied by 2x squared. Plus, then we multiply our last terms together. Negative 4 multiplied by negative 5. Now we just have to simplify each of these products. Now 3x squared multiplied by 2x squared, 3 times 2 is 6. And x squared times x squared is going to be x to the 2 plus 2 power, or x to the 4th power. 3x squared multiplied by negative 5, 3 times negative 5 is negative 15. And the x squared just comes along for the ride. Negative 4 multiplied by 2x squared is going to be negative 8x squared. And finally, negative 4 multiplied by negative 5 at the end is a positive 20. Any questions how I'm multiplying these binomials out here? The two middle like terms need to be combined. Always try to combine like terms if possible, if you have such a situation. So our simplified product is going to be 6x to the 4th. Now negative 15x squared minus 8 more of these x squareds is going to be what? What's negative 15 minus 8?
23.
So it'll be a minus 23 of these x squareds. Notice we're not multiplying these bases together. We're combining like terms. So you keep the variable part the same when you add or subtract like terms. And in doing so, you only add or subtract the coefficients. We're not multiplying these terms together. We're just we're subtracting this monomial from this monomial. Okay, we're combining like terms. So the only time the variable part changes is if you're multiplying like bases, then the variable part changes. But if you're combining like terms, the variable part never changes. Okay? This is plus 20. And we're done. That would be your simplified product of these two binomials up here. And notice this is written in descending order. Okay? Any questions? How we're multiplying binomials together by using our FOIL algorithm, the product of the first terms, the outer terms, the inner terms, the last terms. All right. Okay. All right. Classwork number 1, ladies. I'm going to have you multiply, binomial or two together here. Okay. We'll call this classwork number 1. Now you can just hand this classwork in next week. Don't worry about getting it to me this week. Just bring it to class on Monday and give it to me. So this is February 22nd. I want you to multiply these binomials together here. Here we go. We got x cubed plus 3. I want you to multiply that by x cubed minus 5. Try that one. And then problem number 2 here, you can try this one. 6x minus 5y. I want you to multiply that by 2x minus 3y. Don't forget to combine like terms after you expand out these products here, or multiply them out. All right, go ahead and do that. I'll give you a little bit of time to do that, and we'll check our results. All right, let's take a look here. The first one, we're multiplying x cubed plus 3 multiplied by x cubed minus 5. And you gotta, kind of follow along with the FOIL algorithm. Multiply the first term together, so x cubed times x cubed, plus the outer terms, x cubed times a negative 5, plus the inner terms, 3 times x cubed, plus the last terms, 3 times a negative 5. X cubed times x cubed is x to the 6th power as we add the exponents when we multiply like bases together. X cubed times negative 5 is negative 5x cubed, 3x cubed plus 3x cubed, and 3 times negative 5 is minus 15. These two middle terms here have to be combined. Negative 5x cubed added to 3x cubed gives us a negative 2x cubed. And that would be your answer. Okay, hopefully you've gotten that for your final simplified product of those two binomials. Any questions about that problem there? Multiplying 6x minus 5y times 2x minus 3y, multiplying the first terms together, plus the outer terms together, 6x times negative 3y, plus the inner terms multiplied together, plus the last terms multiplied together. 6x times 2x is 12x squared. 6x multiplied by negative 3y is minus 18xy. Negative 5y multiplied by 2x is minus 10xy, and negative 5y multiplied by negative 3y is going to be a positive 15y squared, because y times y is y to the 2nd power. These two middle terms need to be combined. They are like terms, they're both xy terms. So negative 18 of these xy's subtract 10 more of these xy's gives you negative 28xy. And that's your final answer. Hopefully, ladies and gentlemen, you got these correct. If not, hopefully you can detect the error that occurred. Okay. All right, any questions about any of those there? All right. Now, sometimes these binomials could have like fractions in them, it happens. But nothing changes. We work the same way. So we proceed the same way. So suppose that I have a couple of binomials here. I got 5t minus 1/5, and that's to be multiplied by 10t plus 3/5. Just because we have fractions or decimals from time to time doesn't mean we change the way we proceed. Nothing changes. We still follow the FOIL algorithm. So we're going to multiply our first terms together. 5t gets multiplied by 10t. Plus the outer terms get multiplied together. 5t gets multiplied by 3/5. Plus, then we multiply our inner terms together, negative 1/5 times 10t. Plus then our last terms, negative 1/5 gets multiplied by a positive 3/5. All right. 5t multiplied by 10t, 5 times 10 is 50, and t to the 1st power times t to the 1st power is t to the 2nd power. 5t times 3/5, this all sits over 1, understood. 5t over 1 times 3 over 5. If you're in the cross canceling, you can see that the 5s do cross reduce out to 1s, and you'll be left with 3t. If you're not in the cross canceling, 5t times 3 would be 15t. Over 1 times 5 is 5, but either way, you cut it, slice it, or dice it, this is going to reduce down to 3t anyways. So whether you're in the cross canceling to get 3t or multiply across first then reduce, this is going to be a plus 3t. Negative 1/5 times 10t over 1. A negative times a positive will be a negative, guaranteed. 1/5 times 10t over 1. Again, if you're in the cross canceling, 5 divides into itself once, divides into 10 twice, and you'll be left with 1 times 2t or 2t. Or if you're not in the cross canceling, you'll have 10t over 5. But either way, this is going to reduce down to 2t anyway, so minus 2t. And then finally, negative 1/5 times 3/5. There is no cross canceling available here, so you basically just have to go with it. A negative times a positive is a minus, and 1 times 3 is 3, and 5 times 5 is 25. So negative 1/5 times 3/5 is negative 3/25. We do have two like terms in the middle that need to be combined, and therefore our final simplified product is going to be 50t squared. 3t minus 2t is plus 1t, or just plus t. It's understood there's a 1 there. Minus 3/25, and that is it. That's your answer. That's the product of those two binomials. All right. So, yeah, fractions make things a little messier, but we proceed the same way. We still use the FOIL algorithm to, make sure we cover all the products that are available there. All right. Any questions how we multiply those binomials together there?
Can we do a couple more practice ones?
With what? Fractions? With some fractions?
Yeah.
Yeah, all right. Yeah, sure. Okay, so let's see here. Maybe we got what if we had like 1/3 c minus, let's say, 1/2, and we want to multiply that binomial by this one here, about 3c plus I don't know, maybe like 4/7 or something like that. Okay, messy problem, but nonetheless, we're going to multiply it out the way we multiply any binomials out. Nothing changes there. So 1/3 c's got to get multiplied by the 3c. Now this 3c you can place over 1, understood. You can always put anything over 1, it's still the same thing. Okay? Plus, we multiply the outer terms together. 1/3 c gets multiplied by 4/7. Plus, now we multiply the inner terms together. Negative 1/2, that's a negative 1/2 times 3c. And this 3c I will place over 1 to help me to better deal with this here. Finally, the product of the last terms, negative 1/2 times 4/7. All right. Okay, now we just have to deal with some fractional operations here. 1/3 times 3/1. What's this going to give you? What is 1/3 times 3/1?
Just 1.
Now the 3's cross cancel to 1s, or you could think of it as 3/3. Either way, you're going to walk out of this with what? A value of 1, correct? So 1/3 multiplied by its reciprocal, 3/1, is going to be 1. And c to the first power multiplied by c to the first power is going to be c to the 1 plus 1 power, or c to the second power. So 1/3 c times 3c is 1c squared. What's 1/3 times 4/7? Well, we don't have any cross canceling available, so we go 1 times 4 is 4. And that sits over 3 times 7, which is 21. And then we have the c. Don't lose the c. So 1/3 c multiplied by 4/7 is 4/21 c's. Negative 1/2 times a positive 3c, a negative times a positive will be a minus, so just bring the minus sign down. No cross canceling available, so 1 times 3 is going to be 3, and that sits over 2 times 1, which is 2, and don't lose the factor of c. Bring it along. Finally, we have negative 1/2 times 4/7. A negative times a positive will be a minus. You can do cross canceling if you want to. 2 divides into itself once, 2 divides into 4 twice, and you'll be left with 2/7. Or if you're not into cross canceling, you'll go 1 times 4 is 4, and that sits over 2 times 7, which is 14. But this will reduce down by 2, down to 2/7. So whether you're into cross canceling or not, this will walk out with a value of 2/7. There you go. The only other thing that concerns us here is we have to combine these like terms because they are both c terms. So we have to combine their coefficients. So what's 4/21 minus 3/2? You can do that off to the side of your paper here as we take a trip down memory lane back to basic math. I need a common denominator of 2 and 21, and after a little thought, 42 is the smallest number that's divisible by 2 and 21. Being the case, I have to build both these fractions up into equivalent fractions that both take on the denominator of 42. That means 4 over 21 gets multiplied by 2 over 2 to give me the equivalent fraction of 8 over 42. 3/2 has to be multiplied by 21 over 21 to build it up into an equivalent fraction of 63 over 42. Now, what's 8 40-seconds minus 63 40-seconds? What's 8 minus 63? I believe that's going to be 55. So 55 40-seconds. So therefore, these C terms combine to give us 55 40-second C. So we have C squared plus 55 over 42C. Messy, but that's what it is. And minus 2 sevenths. And that would be your final answer. So again, the thing that confounds us, in this problem is the fractional operations. So we had to go back to basic math and try to jog our memory. How do we work with fractions? Okay.
It would be negative 55 because it was subtracting 63.
Yes, it is. Yeah, it is. You're right. 8 subtract 63 is a negative 55. This should be a minus here. Thanks for bringing my attention to that. That would be a minus there. Yeah, make sure that is a minus. Okay, minus. All right. Any questions? How we mowed through that one there, ladies and gentlemen, dealing with all the fractions. All right. Fractions and decimals just slow us down, but nothing changes as to how we proceed in multiplying binomials together. All right, I want to show you the product of some special binomials now. So sometimes these are called special products, if you will, or a special product. If I have like a binomial A plus B, and I'm going to try to multiply this by another binomial A minus B. Okay. What do you notice about these binomials here? The only difference between these binomials is what? What's the only difference?
One's adding, one's subtracting.
Now we have plus here, and here we have a minus. That's the only difference. These binomials have a name relative to each other. They are called conjugates of each other. Have you ever seen that word before or heard of that? They're called conjugates. Okay. Conjugates. So binomials that differ only by the sign in between the terms are classified as being conjugate binomials. Now we're going to find out what's about to happen here. So I'm going to just multiply this out or FOIL it out, using my FOIL algorithm, the way we did with the other binomials. And we'll see what happens. What's A times A? And ladies and gentlemen, I'm actually going to take a little shortcut here. I'm going to take one training wheel off our bike, okay? I'm not actually going to show the intermediate step that I've been showing. We're just going to kind of do this on the fly now.
Or give me a tooth thing, please.
What's that?
I'm sorry. I didn't know if I was mute.
Okay. So what we're going to do here is I'm going to take A to the first power times A to the first power. And what is A to the first power times A to the first power? It's going to be A to the what power? 1 plus 1 or A to the second power? A squared, correct? A times A is A squared. All right, that's the product of the first terms. Plus, here comes the product of the outer terms. I'm going to take an A here and multiply it by a negative B. I'm going to take a 1A and multiply it by a negative 1B. So 1A multiplied by a negative 1B is going to give me a minus 1AB. Minus 1AB. That's the product of the outer terms. Now the inner terms. What is 1B times 1A? What's 1B multiplied by 1A? Well, that's 1BA, correct? Plus 1BA. True? The product of the inner terms. Now the last terms. What's 1B multiplied by negative 1B? 1B times negative 1B. 1 times negative 1 is what? Minus 1. And B times B. What's B times B? B to the first times B to the first is B to the second. Hey, do you notice what's another name for 1BA? if I just interchange these two or flip these two factors around, isn't 1BA the same thing as 1AB?
Yeah.
Same thing. So let's flip the factors around and let's call this plus 1AB. What do you notice about the two middle terms? What's about to happen to them as we try to combine these two like terms in the middle?
About to
Cancel
vanish.
each other out.
Yeah, they add up to 0. -1 + 1 is 0. So the AB terms drop out of the picture. They cancel out. They add up to 0. In other words, where they're gone. And we're left with a squared minus b squared. Interesting thing occurs when you multiply two conjugate binomials together. You're left with this for a product. You don't have any middle term. Notice, interesting there. So ladies and gentlemen, there's a shortcut here. Instead of having to go through all this in the future, just remember this. I would memorize this right here. This is going to help your cause not only in this course, but in any remaining math courses you take. When you multiply conjugate binomials together, it's an easy thing to do. If you could just remember this pattern. All you do is you square your first terms, square your last terms, and place a minus sign always in between them. And there you go. It's a shortcut if you can memorize that pattern, okay? So I would just commit this to memory. This works for the product of any two conjugate binomials. There, by memorizing this, you don't have to go through all this whole long drawn-out process. The two middle terms will always drop out when you multiply conjugate binomials together. It always occurs. All right. So again, yeah, I would strongly recommend that you just remember that pattern there. That'll speed up your ability to multiply conjugate binomials together. Now they got to be conjugates of each other in order to just go, immediately to this product here. All right, so let's try one out here. If I have a 2a plus a 3b, and I want to multiply this binomial by its conjugate, which is 2a minus 3b, what is going to be the product? These are conjugate binomials because they differ only by the sign in between the terms. Being the case, I don't have to FOIL this all out and go through that whole drawn out process. All I have to do is square my first term, square the last term, and place a minus sign in between them. That would be the product of these two conjugate binomials. It's that simple. And of course, you want to clean this up. You don't want to leave this looking this way because you really need to, square 2a. And to square 2a means 2a times 2a. And 2a times 2a is going to give us 4a squared. Minus 3b squared is 3b times 3b, which gives you 9b squared. And that's your product of these conjugate binomials. So again, I would strongly recommend just memorize this pattern. This is going to come in handy when we go in the reverse direction in the near future, when we learn how to factor polynomials. Given this, we're going to discover this is called the difference between squares, and it always factors into the product of two conjugate binomials. So wise to just memorize that. All right, let's see here. Okay, time check. 11. Okay, I'll try another one like that. We'll multiply a couple more conjugate binomials together. And then I'll give you classwork number 2. Okay, so we're going to try our hand at this one. 3r squared minus 7v times 3r squared plus 7v. Are these conjugate binomials?
Yes.
It does appear that they are. So we don't, in order to multiply these together, we don't have to, multiply it all out. You can if you want, but it's a waste of time. All you got to do is just remember your product of conjugate binomials is always going to be the difference between the squares of the first and the last terms. So all we got to do is this. Shortcut, square your first term, square your last term, and place a minus sign in between them, and that would be the product. So much quicker if you can just remember this pattern here. All right, so therefore, what is 3r squared squared? Well, this is 3r squared times 3r squared, and 3 times 3 is going to be 9. And r squared times r squared Or, ladies and gentlemen, when you raise a power to a power, you multiply these exponents. R squared times R squared will be R to the 2 times 2 power, or R to the 4th power. So 3R squared times 3R squared is 9R to the 4th power, minus 7V squared is 7V times 7V, which gives us 49V squared. V times V, V and V squared. That's your answer. That would be the product of both conjugate binomials. All right, so again, yeah, definitely throw that in the memory banks. How to multiply conjugate binomials together. It's pretty simple. It's just the difference between the squares of the first term and the last term. Okay. So again, 3R squared minus 7V times 3R squared plus 7V. You just square your first term, 3R squared. Square your last term, 7V, and then put a minus sign in between them. We're just following this pattern here because these are conjugate binomials. Okay? And then 3R squared squared is going to be 9R to the 4th. Minus 7V squared is going to be 49V squared. And that's your answer. All right. Okay. Got that there. And again, this is being recorded. So if you miss anything, we have at our hands an opportunity to watch this over again here. What is this telling us to do? Now, temptation has it, when you have a situation like this, is to mess this up. If I have like A minus B and I'm squaring the whole binomial, a lot of us would like to think that it's very simple, nothing more than this, A squared minus B squared. Ladies and gentlemen, this is incorrect. I know it seems, like it should be this way, but it's just not true. When you square a binomial, it's not as simple as just, squaring your first and last terms and putting a plus or minus sign in between them. It's not that easy. It's not that simple. In reality, if you take A minus B and square it, it's really saying to take A minus B times A minus B. And when you FOIL this out, notice these are not conjugates of each other. They're literally the same. They're not conjugates. So we cannot use our conjugate shortcut. So we say A times A is A squared. A times a negative B is minus AB. Multiplying the inner terms together, negative B times A is negative BA. And multiplying the last terms together, negative B times negative B is plus a B squared. So this is going to be A squared minus AB, but negative minus BA is the same thing as if you switch these factors around as another minus AB. It's the same thing. Notice these two middle terms don't drop out. They hang around. In fact, you got to add them together. So what's a negative 1? Subtract 1. What's negative 1? Subtract 1. That's the same thing as negative 1 plus a negative 1, which is going to give you
Negative 2.
yeah, negative 2 of these ABs. And so therefore, be careful, ladies and gentlemen, when you square A minus B, it's not just A squared minus B squared. That's incorrect. It's got to be this. So squaring a binomial, you really should be FOILing it out. Okay, there's not really, any major shortcut per se. So this one here, 3x minus 4y squared is saying 3x minus 4y times itself. And so we will follow along with the FOIL method. So we got 3x times 3x. 3x multiplied by 3x is going to give you 9. What? What's x times x?
X squared.
Outer terms getting multiplied together. We have 3x multiplied by negative 4y. 3 times the negative 4y is a minus 12. And then we have xy. Negative 4y multiplied by 3x. Negative 4 times 3 is a minus of 12. And y times x is yx. But you know what? Another name for yx is xy. So instead of saying yx, let's call it xy. It's the same thing. Finally, multiplying the last terms together, negative 4y times negative 4y. Negative 4 times negative 4 is plus 16. And y times y is y to the 2nd power. Finally, to wrap this up here, we want to combine the two middle like terms as they are like terms. They need to be combined. So minus 12 of these xy's, minus 12 more of these xy's, nets us minus 24 of these xy's. And we're finally done. That would be the correct product of the squaring of that binomial there. Okay. Now, as far as squaring a binomial is concerned, there is a pattern. If you want to take the time to memorize it, it's really not that difficult to memorize. But if you have like a plus b and you're squaring this binomial, well, there is a pattern you could memorize, and it does go like this. It's going to be a squared plus 2ab plus b squared. So, you know, you could throw this into the memory banks also with the product of conjugate binomials if you want. In a similar fashion, a minus b squared will net you a squared minus 2ab plus b squared. So these are worthwhile patterns to also be familiar with. And so in squaring 3x minus 4y up here, I could have used one of my patterns here instead of foiling it all out the long way. So I'm going to do 3x minus 4y again here, squared again. But this time I'm going to make use of one of these patterns. And the pattern I'm going to use is this pattern here, a minus b. So my a is really like a 3x here. My a is like a 3x and my b is a 4y. And so wherever I see a in this pattern, I replace it with a 3x. So 3x replaces this a here. 3x replaces this a here. My b is really a 4y, so 4y replaces the b here. And 4y replaces the b here. All right, now what's 3x squared? 3x times 3x is 9, what? 9x squared? Negative 2 times 3 is negative 6, and negative 6 multiplied by a positive 4 is a minus 24. And we have what? Xy. And 4y squared is 4y times 4y, which is 16y squared. A little bit quicker, do you agree? If you can remember the patterns here. We get the same answer that we got up here, only up here, we what? We foiled it all out, dragged it out a little bit longer here. Got the same answer though. So it's up to you. If I give you a problem like this, want you to square a binomial, you can do it the long way. It's no problem, no big deal. You know, or if you can remember these patterns here, it will speed up the process a little bit here. Okay, it'll speed things up a little bit. But it's up to you how you want to go through that. All right. Sometimes, yes, remembering these patterns can, you know, expedite our ability to multiply some polynomials together. And, you know, knowing these patterns or remembering these patterns is going to become even more attractive when we go in the opposite direction in the near future in this chapter, when we're going to learn how to take a polynomial and factor it back into its factors, going in reverse direction. Then knowing these patterns might pay off more handsomely than they are in multiplying polynomials together. Okay? So feel free if you want to memorize these patterns here. I would probably, if you're going to go onwards and take like college algebra and get into math beyond that, I would just memorize these patterns here, along with the patterns of the what? The product of conjugate binomials. I would throw these into the memory banks, ladies and gentlemen. It's only going to aid your ability to factor and multiply polynomials together quicker. All right. All right, you ready for classwork 2? All right, classwork number 2, I want you to see if you can deal with these binomial products here. So for problem number 1, I'm going to say simplify. And the first one is going to be, let's see here. Okay, I'm going to have 3m minus 4n times 3m plus 4n. See if you can, you know, come up with the correct product of these binomials, and it would be great if you could maybe use an appropriate pattern to speed things up here. If you can't remember the pattern, feel free to FOIL it all out. You'll get the same answer in the end, but a pattern will expedite things. Try that one there, and let's see if you can maybe also do this one here. X squared plus 6 squared. Okay, so see if you can simplify this one here. All right, so there we go. We'll call that classwork number 2. Okay. And again, these classworks you can turn in on Monday. Assume we have class on Monday. All right, now what do you notice about these first binomials here? These are what, conjugates of each other, because they only differ by the sign in between the terms. And to multiply these together, you know, you're welcome to use the pattern that I've been advertising. When you got A minus B in general times A plus B, the product is simply the square of the first term minus the square of the last term of your binomials. It's that simple, if you can just remember that pattern. So therefore, this product is going to be the square of the first term minus the square of the last term. That's it. That's as simple as the product is. So much easier if you just remember the shortcut here. This is therefore going to be 9m squared minus 4n squared. And ladies and gentlemen, that's your answer. It's that easy because these are conjugate binomials. Very easy to multiply conjugate binomials together. All right, and hopefully you've gotten that. We're good on that. Now here you can, if you want, multiply this all out the long way using your FOIL algorithm, or ladies and gentlemen, we can make use of a pattern to speed things up just a tad. If you can remember this pattern here in general, it'll enable you to, you know, get this product a little quicker. Of course, this pattern is the square of the first term plus 2 times the first and the last term plus the last term squared. That's the pattern.
Hey, can you go back up to the top?
Yeah. Up
How
here?
did you get 4n squared? I thought it was 16n squared.
Wait a minute. That should be 16n squared. My gosh, I am not having a good day. Maybe it's a good thing I didn't try the roads today. All right, you are correct. Yeah, 4n squared is 16n squared. Sorry about that. All right, everything else looks good.
All right, thank you.
Yep, not a good day. I am not having a good day. All right, I don't know what's going on. Now, here we're trying to square a binomial, and you are welcome to use this pattern to, speed this up a little bit. If you don't want to, you can just, multiply this out the long way, x squared plus 6 times x squared plus 6. It'll work. You'll still get the same answer, so you can always fall back on this if you don't remember the pattern. But I'm going to try to implement the pattern here. My a is really an x squared. My a is really an x squared here. So my a is really like an x squared here. My b is really like a 6. So wherever I see an a in this pattern, I replace it with an x squared. Wherever I see a b in this pattern, I replace it with a 6. All right. So now what's x squared squared? X squared times x squared, that's what this is saying, is going to be x to the 4th power. 2x squared times 6, 2 times 6 is 12, so this will be plus 12x squared. And then plus 6 squared, hopefully I'll get this correct, 6 times 6 is 36. And that would be your final answer. So x to the 4th power plus 12x squared plus 36 is the product of squaring this binomial. All right. All right. Hopefully, ladies and gentlemen, you are experiencing some success out there in multiplying polynomials together. All right. It is now 1:30. I think it's time to start addressing how to divide polynomials in section 5.3. Division can be easy, but there are problems where it's more involved. Okay. So we will put away section 5.2 and finish up today with section 5.3. Dividing polynomials. Okay. All right. The first one I'm going to show you is how to divide in general a polynomial by a monomial. Dividing by monomials. Six x cubed so I'm going to try to take this polynomial or this trinomial and divide it by this monomial. To do that is pretty simple. Whenever you divide a polynomial by a monomial, you can just utilize something we've known all along since basic math. And that is the case of if I have a plus b over c, ladies and gentlemen, this came from the fact that I had a over c plus b over c. Isn't that true? Back in basic math here. Back in basic math, we went this way, correct? When you're dividing a polynomial by a monomial, you can go this way. Meaning that I can take each term of this trinomial and place it over the monomial divisor. So I can take my 6x cubed and I can place it over 3x. Plus I can put the 12x squared and I can place that over 3x. Plus I can put the negative 9x and place that over the 3x. This is equal to this. So I split it up into 3 different fractions here. Now to the party, we have to bring another property of exponents if we are to be successful in dividing polynomials. And that extra property that we must bring into play here is this property here. Notice in the last section, we had to entertain the property where we multiply 2 bases, like bases together, we add the exponents. What happens when we divide like bases? What do we do with the exponents? Anybody remember?
Subtract.
We're going to subtract the exponents. So therefore, we keep the base the same and we subtract the exponents. Notice my order of subtraction. I'm going to take the numerator power and subtract off the denominator power. Okay. This is the property that we must import into section 5.43 in order to be successful in dividing polynomials together. Got to know that. All right, here we go. Now, 6x to the third power divided by 3x to the first power. What's 6 divided by 3? Let's reduce the coefficients first. 6 divided by 3 reduces down to what, 2?
2.
And then x to the third power divided by x to the first power is going to be x to the 3 subtract what? 1 power. Plus 12x squared divided by 3x to the first power. Reduce the coefficients first. 12 divided by 3 is 4. X squared divided by x to the first power is going to be x to the 2 minus 1 power. Finally, negative 9x divided by 3x, negative 9 divided by a positive 3 is a minus 3. And what happens to the x's? Well, technically, ladies and gentlemen, x to the first power divided by x to the first power, we do subtract the exponents. It'll be x to the 1 minus 1 power. I'll get back to this in a moment and tell us what to do with that. So we have 2x squared plus 4x minus 3 technically times x to the 0th power. But you know what? It's a well-known fact also in mathematics that if we raise any non-zero quantity to the 0th power, we always get what? 1. This is always true, provided, of course, we don't raise 0 to the 0th power because that's called an indeterminate form. But you raise any other quantity to the 0th power, it's always 1. So in other words, this is like minus 3 times 1 at the end. This is 1. This is 1. And it makes sense why it's 1, because anything divided by itself reduces down to 1. X divided by x is 1. So in the future, do we have to go through all this jazz here? No, we don't. Just say the x's reduce out to 1s. So we're just left with minus 3 at the end. All right, so here we go. So we got 2x squared plus 4x minus 1, and we're done. This would be the quotient of having divided this trinomial by this monomial. Now we understand what just happened there. So when you divide like bases, you keep the base the same and you subtract the exponents. Okay? That's the property we need to bring into this situation here.
Yeah, my question is, how did you get the 1 instead of it being 3?
That's my question too.
Because I'm having a Monday. Yeah, it should be a minus 3 times 1, which is minus 3. You know what's bizarre? It actually is scary. I never used to make these little subtle mistakes before. I hope it's not, you know.
I think you're testing this.
Well, I mean, I just hope it's not a prelude of things that are bad things that are heading my way as far as my health is concerned, because this is weird. I never used to make these little mistakes. So it's kind of scary. I don't know why I'm making these little mistakes today. But do we understand what's going on here so far? Aside from my little glitches, okay? All right. Okay, let's maybe try one more here, or do you guys want to try one? I think we're up to classwork number 3 now. You want to have a go at this one here? Call it classwork 3. Take 6y to the 4th minus 3y squared, 3y cubed rather, plus 18y squared. And I want you to divide this trinomial by this monomial, 9y squared. Okay, so the instructions here will say simplify, or your instructions could say divide. As that's what we are being asked to do. Divide a polynomial by a monomial. Go ahead and do that. Give you maybe a minute or two. See if you can crank out that quotient there.
7. Y to the third plus my calculator. Mm, 52. That's 54, right? Yeah, 54Y.
All right, what we do when we divide in general, polynomial by a monomial, is we split it up into separate fractions by placing each term of the polynomial over the monomial denominator. And then we got to reduce 3 fractions here. Now 6/9 reduces down by 3 down to 2/3. Y to the 4th divided by y to the 2nd is y to the 4 subtract 2 power, or y to the 2nd power. The next term is going to be a minus. 3 divided by 9, or 3/9, reduces down by 3 down to 1/3. Y to the 3rd divided by y to the 2nd is y to the 3 minus 2 power, y to the 1st power. Finally, these y squares at the end reduce to 1. Just get rid of them. Cross them out. They reduce to 1. And then 18 divided by 9 reduces down to 2. And that would be your final answer. Okay, just like that. And we understand how we're dividing a polynomial by a monomial in general here. It's that simple. Just split it up into separate fractions, reduce each of the fractions individually, you got your quotient. So that's all there is to it. All right, ladies and gentlemen, there's bigger fish to fry, and we got to move on. The bigger fish to fry is how to divide a polynomial by a binomial. Now, this is much more difficult, okay? More involved. Dividing a polynomial by a binomial. More involved. The first method I'm going to show you is called long polynomial division. And I'll show you a shortcut in certain cases called synthetic division. All right, there we go. We're going to dive right in. We're going to take this x squared plus 4x minus 8. We're going to try to divide this trinomial by this binomial x minus 3. So that's what we're going to try to do here. So the instructions here will say simplify or divide. Now, unlike dividing a polynomial by a monomial, like if this was just over x, I could split this up into 3 different fractions and reduce each of the 3 fractions. Can't do this now because this is not a monomial, it's a binomial. So this is more involved. In fact, splitting it up by putting x squared over x minus 3, 4x over x minus 3, and negative 8 over x minus 3, that's not going to help us at all. That's not going to get us anywhere. Now, ladies and gentlemen, in order to do this, we're going to have to use what's called long polynomial division. So I'm literally going to have to take my divisor, which is x minus 3, put it outside of my long division bar. Yep, the same bar you see in basic math. And my dividend is going to be the trinomial. It's going to slide underneath this division bar. And now we're going to have to go through what is called long polynomial division. All right, now a couple of things to note. Notice both my divisor and dividend are written in descending order. So requirement number 1, when you do this long polynomial division, both divisor and dividend must be in descending order. If they're not, you have to get them in descending order first. That's requirement number 1. Requirement number 2 is you need to have all the variables present with both divisor and dividend. And notice I do have all my variables present. I got a first degree term in here and a 0th degree term. We're not missing any powers of x in here. The dividend has all the powers of x too. I have a second degree term in x. I have a first degree term in x, and I have a 0 degree term in x. We're good. So now we can begin our division. And so how do we begin? Well, round one of division. I ask myself, how many times is x divided into x squared? You know, to answer that question, off the side of your paper, you're welcome to do this, although you don't have to do this. You're welcome to do this, though. I like to call this round number one of division. By placing x squared over x and reducing this, I'm going to find out what my first term and my quotient is. So how does x squared over x reduce? X squared divided by x to the first power is x to the 2 minus 1 power, or x. X is going to be the first term in my quotient. Now, oddly enough, the way most textbooks show this is authors like to leave like terms lined up in columns. So it's strange because you would think that we'd put the x above the x squared because we divided x into x squared. Your author's not going to do that. Because your first term of your quotient is x, your author's going to put it above the 4x because your author wants to leave like terms lined up in columns when performing long polynomial division. Now, here's what we're going to do. We got to take this x and multiply it by the divisor. So this x has to get multiplied by x minus 3. So what's x times x? That gives you x squared. We slide it underneath this x squared. What's x times negative 3? That gives you minus 3x. Slides underneath the 4x. Then we subtract off this whole polynomial. This algorithm is going to work the same way as if we're dividing whole numbers back in basic math using long division. The algorithm remains the same. It's just that we got variables to worry about now. Now, what's x squared subtract itself? The x squareds drop out of the picture. They're gone. What's 4x subtract a negative 3x? If nothing else, what's going to get you when you do this is sign mistakes. So be careful of your signs. What's 4 subtract a negative 3? 4 minus a negative 3 is really 4 plus 3, which is really what, 7? Everybody see that there? So 4x subtract a negative 3x is going to be 4x plus 3x, which is 7x. Drop down the next term as we set ourselves up for round 2 of division. You got to drop the minus 8 down. And now we're ready for round 2 of division. Round 2. We ask ourselves, how many times is x here divide into 7x? To answer that question, we put the 7x over x and reduce this. You'll have your answer. How does this reduce? With 7x over x. Reduces.
Wait,
what's that?
How did you get this 7x? That's you lost me there.
4x subtract a negative 3x. 4 subtract a negative 3. What's 4 subtract a negative 3? That's really 4 plus 3. Subtracting a number is like adding the opposite, correct? Have you ever learned it that way? So when you subtract a number from another number, it's like adding the opposite of the number being subtracted. Okay. So subtraction is really like adding the what? Adding the opposite. Everybody see that there? So 4 minus a negative 3 is 4 plus a what? Positive 3, which is really what? A positive 7. That's the way it works out. It's not 4 subtract 3. No. It's 4 subtract a negative 3, which is 4 plus a positive 3, which is 7. All right, so that's a positive 7. So 4x subtract a negative 3x is 4x plus 3x, which is 7x. And then we bring the minus 8 down. All right, how many times is x divided into 7x? 7x over x reduces down to what, 7? So plus 7 becomes the next term in our quotient up here. This is our answer we're forming up here. It's called our quotient. We take the 7 now and multiply it by the x minus 3. Take the 7 and multiply it by your divisor, x minus 3. 7 times x, 7x. Slide underneath the 7x. 7 times negative 3, negative 21. Slide it underneath the minus 8. And then we have to subtract off the whole polynomial. Now, what's 7x minus itself? What happens to the 7x's here? 7x minus 7x is 0x. In other words, the x's are gone. Careful here. What's a negative 8? Subtract, not 21. No. It's negative 8 subtract a negative 21. What's a negative 8 minus a negative 21? Well, that's the same thing as changing subtraction to addition and adding the opposite. What's the opposite of negative 21? Positive 21? That's really what we're having to do here. Negative 8 subtract a negative 21 is really negative 8 plus a positive 21. And a negative plus a positive means we take the difference between the numbers and attach the larger sign. This gives you what, 13? Would it be positive or negative 13?
Positive 13.
Positive 13. This is the larger of the two numbers and it's positive. So this has to give you a positive 13. So as it turns out, negative 8 subtract a negative 21 is really negative 8 plus 21, which really nets us a positive 13. Back to the problem. Therefore, a negative 8 subtract a negative 21 is really a positive 13. Notice we have nothing else to bring down. And since we have nothing else to bring down, our division algorithm has terminated. We're done. This is called your remainder. Here's what we should do. We should say plus in our quotient, put a plus sign, bring your remainder 13 up and place it over the divisor. And you're looking at your entire answer here. This is your quotient. So ladies and gentlemen, after having divided this trinomial by this binomial, our quotient is going to be x plus 7 plus 13 over what? X minus 3. This is your answer. This is your quotient. That's called long polynomial division. And this requires practice to get good at this because there's a lot of steps. All right. But with practice, you will perfect this. And then it just becomes very repetitious. All right. Maybe we better do another one. In fact, I wish I had time to do maybe another 1,000 of these, but time does not permit me to do that. But I'll try another one, okay? Let's try this one. The more you do, the better you're going to get. Practice is critical for success in mathematics. Take this trinomial, try to divide it by this binomial using long polynomial division. So here we go. Here's my 2x minus 7. My dividend is the trinomial. It slides underneath my long division bar. And we are ready to begin our long polynomial division here. Notice both divisor and dividend are written in descending order. Secondly, notice I'm not missing any powers of x here, first degree term, 0 degree term. No powers missing for x in here also, second degree, first degree, 0 degree term. We're ready to begin our division. We ask ourselves, round number 1, how many times is 2x divided into 8x squared? Feel free to take the 8x squared off to the side of your paper and place it over 2x and reduce this. You'll have your answer. How does 8x squared over 2x reduce? What does that reduce down to? This reduces down to what? 4x? So 4x becomes the first term in your quotient. So as to keep like terms lined up in columns, I don't put the 4x above the 8x squared, although we did divide 2x into 8x squared. Ironically enough, we put above the 26x because authors like to leave like terms lined up in columns. We take the 4x, multiply it by our divisor now. When you get better at this, you can forego this step, this little training wheel, and also this little training wheel. You get rid of all this. And you can fly through this more seamlessly, but that takes practice to get to that level. Now, what's 4x times 2x?
8x squared.
8x squared slides underneath the 8x squared. What's 4x times negative 7? Minus 28x slides underneath the minus 26x. We must subtract off the whole polynomial. Look, if I do this, I made a mistake. What's the big mistake I made here? I made a huge mistake. This looks like I'm only to subtract off the what, 8x squared. Do you agree? That's a mistake. We got to subtract off this whole polynomial. Make sure you always put it inside parentheses. Got to minus the whole thing off. Now here we go. What's 8x squared minus itself? 0, right? The 8x squareds are gone. What's a negative 26x subtract the negative 28x?
I got one question for you.
Yeah, go ahead.
Before we go any further, how you get a negative 8? You multiply by a positive, didn't you?
Yeah, I multiplied 4x by 2x and got 8x squared. But we are to subtract off this whole polynomial.
Oh, yeah, okay.
Part of the algorithm, correct? You always subtract the whole thing off there.
Yeah, all right, I'm good.
Okay. Now, what's a negative 26x subtract the negative 28x? So what it comes down to is, do we know how to do this minusing with all these signs here. What's a negative 26 subtract a negative 28? That's what it's coming down to right here.
2.
Isn't that negative 26 plus 28? Yeah, you're right. Doesn't it give you 2? Okay, that gives you 2. All right. So therefore, negative 26x minus a negative 28x is really 2x. Bring down to negative 9 as we set ourselves up for round 2 of division. And now we're ready for round 2. We ask ourselves, how many times does 2x divide into 2x? Off to the side of your paper, feel free to take the 2x and place it over the 2x and reduce. You'll have your answer. How many times does 2x divide into 2x?
1.
One time. So plus 1 becomes the next term in our quotient up here. Plus 1. We take the 1 now and multiply it by our divisor. So 1 times 2x minus 7. So 1 times 2x, 2x. 1 times negative 7, negative 7. Subtract off the whole polynomial. What's 2x minus itself?
0.
Gone. 2x's are gone. What's a negative 9? Subtract a negative 7. Negative 9 minus a negative 7. Isn't that really equivalent to negative 9 plus 7? Which is really what? Negative 2?
Negative 2.
Notice we do not have a 0 remainder like the other. Well, we did have one before. But anyways, we do have a remainder and we have nothing else to break down. So our division algorithm has terminated. We're done dividing. But we want to bring this remainder up. I could say plus in my quotient, bring the remainder up to negative 2. And I can put the negative 2 over the divisor, the 2x minus 7. And this entire thing is called your quotient. So your entire quotient, after having divided this trinomial by this binomial, is going to be 4x plus 1. Now, instead of saying plus a negative 2 over 2x minus 7, a more compact way of combining these signs is just to say minus 2 over 2x minus 7. Minus 2 over 2x minus 7. There's your answer. That's your quotient. Okay. Called long polynomial division. It's not a favorite among students. You can see why. It does have quite a few steps. But again, with practice, we are going to get better. And the key is practice. I mean, you need to do as many of these as you need to do to you get it down to where you feel comfortable with this whole process here. All right. But once you get it down and, with practice, not only does this become more proficient and you become better at it, but it actually gets to the point when you do enough practice where this becomes just downright enjoyable. Where you can't get enough of these things. Okay. All right. Let's try this one now. All right. So I'm going to try to divide this 4-term polynomial by this binomial here using long polynomial division. So here's my divisor. And you guessed it, my big old 4-term polynomial is going to slip underneath the division bar as my dividend. And we seek the quotient, the answer, which is going to be up here. Okay. All right, so we got to divide. Notice I'm not missing any powers of x in both my divisor and my dividend, and both are written in descending order. 1st degree term, 0 degree term, 3rd degree term, 2nd degree term, 1st degree term, and 0 degree term. We're good to go here. Round 1. I ask myself, how many times does x divide into 3x cubed? Feel free to take the 3x cubed, place it over the x, and reduce. You'll have your answer. What is 3x cubed over x reduced down to? Well, that's going to be 3x what? 3x to the 3 minus 1 power of 3x squared? That's the first term in your quotient, 3x squared. I'm going to put the 3x squared above the 5x squared because authors like to line up like terms in columns. Take the 3x squared and multiply it by your divisor. 3x squared times x, 3x cubed. 3x squared times a negative 2 minus 6x squared. Subtract off the whole polynomial. What happens to the 3x cubed? 3x cubed minus itself is 0. Those are gone. What's a negative 5x squared? Subtract a negative 6x squared. Uh-oh, here we go with this stuff again. What's negative 5 subtract a negative 6? That's really negative.
Squared.
What's that?
That's really x squared, right?
That's right. Because negative 5 subtract a negative 6 is really negative 5 plus 6, which is positive 1. 1x squared. You are correct. Or you just say x squared. Same thing. Bring down the next term as we set ourselves up for round 2 of division here. And now we are to round 2 now. We ask ourselves for round 2, how many times does x divide an x squared? To answer that question, feel free to put the x squared over x and reduce this. That reduces down to just x. So plus x becomes the next term in our quotient. Take the x, multiply it by the divisor, and what do we get? X times x is x squared, or 1x squared, same thing. 1x times -2 minus 2x. Subtract off the whole polynomial. What happens to the x squareds? They're gone. What's a 2x subtract a -2x? Don't say 0x. This is not 2x subtract 2x. No. It's 2x subtract a -2x.
That's correct.
That's going to be 2x plus 2x, which is 4x. So you really got to be careful with your signs. Sign mistakes are the most common culprit when trying to do long polynomial division. Bring down the next term to -1 as we set ourselves up for the last round of division.
Better.
We got one more round now. This is round 3. We ask ourselves, how many times does this x divide into 4x?
4.
4 times. Plus 4 becomes the next term in our quotient up here. Take the 4, multiply it by the divisor. 4 times x is 4x. 4 times a -2 is a -8. Subtract off the whole polynomial. Subtract the whole thing off. 4x minus itself, the x's are gone. -1 subtract a -8. -1 subtract a -8 is really equivalent to -1 plus the opposite of -8, which is +8. And -1 plus a +8, you take the difference, attach the larger sign, it's going to be a +7. 7's your remainder. Go to your quotient, put a plus sign, bring your remainder 7 up, put it over the divisor. You have your entire answer. This is your quotient. This whole thing is your quotient here. Okay. So your quotient is 3x squared plus x plus 4 plus 7 over x minus 2. That's your entire quotient. That's your answer. So do you think with practice, ladies and gentlemen, you're going to get better at this long polynomial division?
Definitely.
With practice. The key is practice. But you can see it really is a repetitious algorithm. It just repeats. It cycles through. It's really not that bad once you get used to it. Just get used to all these steps. And that comes with practice. Okay. All right. Now, I need to show you one like this. I got to show you one like this so that you don't freak out when you run into one of these in your homework.
It's going to be a fraction.
Because then you're going to wonder, who do I call? You know what I'm saying? It's not the Ghostbusters. We're going to try to divide here, okay? All right, ladies and gentlemen, we're going to try to divide y to the 4th minus 81 by y minus 3, this binomial y minus 3. All right, now here we go. We're going to try long polynomial division here. I'm going to put my y minus 3 outside. It's my divisor, and my dividend is going to slip underneath here. Okay, now, here's the kicker. Notice I have all my powers of y in my divisor, 1st degree term, 0th degree term. And my dividend's written in descending order too, 4th degree term, 0th degree term. But guess what? My dividend is lacking something. In fact, it's missing quite a few things. Notice I go from a 4th degree term automatically down to a 0th degree term. You know what I'm missing inside here in between these two terms? I'm missing a 3rd degree term in y. I'm missing a 2nd degree term in y. And I'm missing a 1st degree term in y. We need to therefore insert what are called placeholders in order for this division to work out. So here we go. Here's what we're really going to have to do is this problem. We got to divide y minus 3 into this polynomial. Y to the 4th. Here comes the placeholder for the 3rd degree term in the form of 0y cubed. This is called a placeholder. It doesn't change the value of my dividend. It just holds a place. Because 0 times anything is as good as if this is not even here. But we do put it here because it's a placeholder. Plus, we're missing a second degree term in y, so we have to insert another placeholder, plus 0y squared. We're also missing a first degree placeholder term in y. And then we got our constant term at the end. These are called placeholders, and they are necessary in order to enable our division to line up properly. If you don't put these placeholders in here, it's not going to work out. Things are not going to line up. All right, so this is critical to put your placeholders in here. Now we're ready to begin our division. Round one. We ask ourselves, how many times does y divide in y to the fourth? It divides in y cubed times. So y cubed is the first term in my quotient. Take y cubed, multiply it by the divisor, and what do we get? Y cubed times y is y to the fourth. Y cubed times -3, -3y cubed. Subtract off the whole polynomial. You see why you needed that placeholder up here? Because where would you put the 3y cubed? You can't put it underneath the constant term. You got to put it underneath its like term counterpart. That's why you have to have this placeholder here. All right, now we subtract this off. What's y to the fourth minus y to the fourth? Y to the fourths are gone to 0. What's 0y cubed subtract a -3y cubed? What's 0 subtract a -3?
We're adding.
That's really 0 plus 3. That's really positive 3y cubed. Bring down the next term as we set ourselves up for the next round of division. All right, here goes round 2 now. We ask ourselves, how many times is y divided into 3y cubed? Well, after reducing this, we've discovered y divides into this 3y squared times. That becomes the next term in your quotient. Take the 3y squared, multiply it by the divisor. 3y squared times y, 3y cubed. 3y squared times -3, -9, excuse me. Whoa. Almost fell into my Monday trap. 3y squared times -3 is -9y squared. Subtract off the whole polynomial. What happens to the 3y squared, 3y cubes here? They drop out to 0. What's 0y squared subtract the -9y squared? That's really 0 plus 9y, 0 plus 9, which is positive 9, so 9y squared. Bring down the next term as we set ourselves up for round 3 of division. And here we go. We ask ourselves, how many times is y divided into 9y squared? Take the 9y squared, place it over y, reduce, and this reduces down to 9y. Plus 9y becomes the next term in your quotient. Take the 9y, multiply it by your divisor, and what do we get? 9y times y is 9y squared. 9y times -3 is -27y. Subtract off the whole polynomial. Now, 9y squared minus itself is 0. 0y subtract a -27y is 0y plus 27y, which is 27y. Bring down to -81. Here's the last round of division. And we ask ourselves, how many times is this y up here divided into 27y? Divides in 27 times, do you agree? Plus 27 now is the next term in our quotient. Take the 27, multiply it by the divisor, and what do we get? 27 times y, 27y. 27 times -3, -81, I believe. Subtract off the whole polynomial. 27y's drop out to 0, and the -81s drop out. Notice -81 subtract itself is really like -81 plus 81, which is 0. 0 remainder, done. This is your quotient. That's your answer right there. So this is called long polynomial division, ladies and gentlemen. What do you think about it? With practice, you think you might perfect this skill. All right. Would you believe in your second semester of calculus, there are times when you have to use long polynomial division? Yes, it does occur. Okay, it does happen. All right, so this is a skill that comes back to visit you later on in math. All right. Now, I'm going to show you something really beautiful here, ladies and gentlemen. You remember this problem that I did here? By taking this trinomial and dividing it by this binomial here, this is the answer we got, correct? That was our entire quotient there.
Yeah.
You know what? I'm going to do this problem over again, but I'm going to show you a shortcut, a marvelous, compact way of dividing a polynomial by a binomial. It's called synthetic division. You're going to love it. You are going to love it. What synthetic division does is it takes this long polynomial division algorithm and it basically compresses it down into one line. It compresses all this madness into one line. It's called synthetic division. It's an amazing quick way of dividing a polynomial by a binomial. And I'm going to demonstrate, I'm going to work this problem over again using synthetic division and convince ourselves we get the same answer that we got when I used long polynomial division. Okay. So here we go. It's called synthetic division. All right, synthetic division. Now, this is a requirement for synthetic division, though. It does have a little bit of a requirement. The divisor, ladies and gentlemen, the divisor must be of the form of x minus c, where c is some real number. It has to be of this form. Your divisor must look like this in general, okay? That is a requirement, and that is a little bit of a restriction, okay? That does not enable synthetic division to work for all cases. But it will work for any divisor that looks like this. And you agree that my divisor x minus 2 looks just like that? Isn't that true? Doesn't my x minus 2 fit the bill here for my divisor x minus c? It works, doesn't it? Okay. So here's what we're going to do here. When you do synthetic division, what you do is you divide this number c synthetically using an upside down division bar into the coefficients of the dividend. And what's going to happen is your quotient's going to actually appear below this upside down division bar, quotient. And at the end, you're going to have what's called a remainder here. That's what synthetic division looks like. It compresses long division down to basically one line, if you will. Okay. So here we go. We're going to employ this new method of dividing by a binomial called synthetic division for this problem here that I worked out earlier using long polynomial division. And we're going to convince ourselves we get the same answer. So here we go. What I'm going to do is I'm going to try to take 3x cubed minus 5x squared plus 2x minus 1. And I'm going to take this big old polynomial here and try to divide it by this divisor or binomial divisor of x minus 2. We're going to rework this problem. But we're going to do this synthetically or using synthetic division. Remember, my divisor has to be of the form of x minus c, and the number I divide into the coefficients of my dividend must be that number c. So what am I going to divide in? What number do I divide in? Do I divide in -2 or +2?
-2.
No,
No, positive.
Yeah, it's +2 because my divisor is of the form of x minus c. And when it's in this form, you literally just divide the number c in, not -c, but c. Okay. If this was x plus c, then you would be dividing -c in, -c. So just remember it this way. You always divide in the opposite of what sign you see here. If we see a minus sign, we divide +c in. If this was a plus sign, you would divide -c in. Everybody see that there? It's just the opposite. Right? But we divide a +c in when our divisor is of the form of x minus c. Okay. So I'm going to divide a +2 synthetically into the coefficients of this dividend. When you do synthetic division, you don't see any variables. All you see are numbers. Gone are the variables. Notice I have all my powers of x, though. You don't have to put any placeholders in here. 3rd degree term, 2nd degree term, 1st degree term, 0 degree term. So we just put our coefficients in here. And ladies and gentlemen, we bring this down and we're ready to begin our synthetic division. It is this simple. You are going to love this. Here's what you do is you multiply, you bring the number up and you add. Multiply, bring number up, add. Multiply, bring number up, add. That's all there is to synthetic division. So what's 2 times 3? 6. Bring the number up, now add. What's negative 5 plus 6?
1.
It's a positive 1. We multiply 2 times 1, bring the number 2 up, add. 2 plus 2, 4. Multiply 2 times 4 is 8, bring the number up, add. You get 7. We are done. This is your remainder. Recognize it? That's your remainder. And so here's what we've accomplished. We've taken a 3rd degree polynomial and we've divided it by a 1st degree polynomial. That means our quotient is going to be of what degree? When you take a 3rd degree polynomial and divide it by a 1st degree polynomial, your quotient is going to be of what degree?
Degree.
It's going to be of what? 2nd degree, is it not? Oh, I'm sorry. Isn't it going to be of the 2nd degree? True. When you divide a 3rd degree by a 1st degree. So how are we going to get our quotient? Well, here's how. You're staring at your quotient in the bottom line here. Our quotient is going to be 3x squared plus 1x plus 4 plus my remainder 7 over my divisor, which is x minus 2, done. Ladies and gentlemen, did I or did I not get the same quotient when I divided this polynomial by this binomial using long polynomial division? Did I not get the same answer? Let's check it out. Oh, there it is. Same answer, only a lot longer. Do you agree? Synthetic division has collapsed this down to one line, and we get our same answer, only a heck of a lot more quicker. Okay, that's called synthetic division. You got to love it. Maybe we'll try another one. Okay, synthetic division.
Can that be used in like all the long division?
Yes, as long as your divisor again looks like this, like x minus c though, okay? You see, it becomes more complicated if your divisor is like of the form of like 2x plus 7. Then it becomes a big problem. You know what I'm saying? No good. All right. All right, let's try another one here. Let's try this one here. If I take x cubed minus 81, and I want to divide this by x, let's say, how about x cubed plus 81? I want to divide it by x plus 3. Okay. But this time, let's suppose that we want to divide it synthetically, not using long polynomial division. So here we go. Here's our upside down synthetic division bar. What do I divide in? My divisor is x plus 3. But do you agree x plus 3 technically is really x minus a what? Negative 3? Isn't that true? So what am I going to be dividing in here, ladies and gentlemen? If I got to divide in,
3?
yeah, I'm going to be dividing in a negative 3, not a positive 3, a negative 3. Because my binomial divisor has to be of the form of x minus c. My c is literally a negative 3 here. You see that there? We divide a negative 3 in. Just remember this way. Look at it. You always divide the opposite sign in. If this is a plus, you divide the negative 3 in. If this is a minus 3, you divide positive 3 in. That's all there is to it. Now, here we go. What's my coefficients of my dividend? Notice I'm missing some powers of x in here. I'm missing a 2nd degree term and a 1st degree term as I go from a 3rd degree term down to a 0 degree term. We have to put some placeholders in here. And here's how we do it. My leading coefficient is 1. This is the 0 for the term 0x squared, placeholder. Then we have to have another 0 placeholder for my 0x term, my 1st degree term missing in here. And then I got my 81, which is the constant at the end. Everybody understand this here? This is my 3rd degree term. This is my 2nd degree term, my 1st degree term, and my constant. I had to put 2 placeholders in between here because I'm missing my 2nd degree and my 1st degree terms in x. Bring the 1 down, and here we go. What's negative 3 times 1? Negative 3, and then we add. What's 0 plus a negative 3? Negative 3. What's negative 3 times negative 3? Positive 9, and we add. What's 0 plus 9? 9. We multiply. Negative 3 times 9 is negative 81. Bring the number up, add. What do we get for a remainder? We get a 0 remainder. We're done. Here's your
Wait, can you
quotient.
do that? Can you start from the beginning again? Can you redo that from the beginning? The 3 and a 1?
Right up here, I'm dividing by x plus 3, so I have to divide in not positive 3, but what? Negative 3, okay? And I'm dividing negative 3 into the coefficients of my dividend here. My leading coefficient's 1, but I'm missing a second degree term in x in here, so I must have 0 for a placeholder. I'm missing x to the first power in here also, so I have to add another placeholder in the form of 0x, in the form of just 0. And then my constant 81. So here we go. Bring the 1 down. We go negative 3 times 1. What's negative 3 times 1?
Oh, negative 3.
No, what's 0 plus a negative 3?
Negative 0.
0 plus a negative 3.
Oh, negative 3.
What's a negative 3 times negative 3?
Oh, that's 9.
0 plus
Oh,
9.
no, that's positive 9.
Yep. Negative 3 times negative 3 is positive 9. And what's 0 plus 9? 9.
Yep.
And what's negative 3 times wait a minute. Where did
Ain't
yeah.
that
Yeah, what's
27?
negative 3?
27.
That's negative 27.
Negative 27. All right, hold on. That's no good. Scrap that. No, what was that one I did here? Yes, here it is right here. Let's try this one. Y to the 4th minus 81 divided by y minus 3. We'll try this one synthetically. Okay, so what am I going to divide in? Positive or negative 3? The opposite of this. Positive 3. The opposite of this. You divide in positive 3. What are my coefficients of my dividend? I got 1. That's my 4th degree term, but I'm missing a 3rd degree term in y, so I must have a what? Placeholder 0. I'm missing a 2nd degree term in y, another placeholder needed. I'm missing a 1st degree term in y, another placeholder needed. And I got my constant term, my 0 degree term, which is negative 81. There we go. Now we're ready to begin our division. All right, help me out here. What's 3 times 1?
3.
0 plus 3 is 3. 3 times 3.
9.
Add 9. 3 times 9.
27.
Add 27. 3 times 27. Positive what? 81. Do you agree? And when you add these together, what do you get?
0.
0 remainder. What's my quotient? Notice I took a 4th degree polynomial and I divided it by a what? 1st degree binomial. Therefore, my quotient polynomial must be of what degree? What's 4 minus 1? Must be of 3rd degree. Do you agree? Here we go. Here's your quotient. 1y cubed plus 3y squared plus 9y plus 27 with a remainder of 0. This is your answer. That's your quotient. Isn't this synthetic division beautiful?
They're way better than long division.
It's a lot faster than long division. You got to admit. Now, you could have done this by long division. You get the same answer in the end. Convince yourself. Try that outside of class. Divide this long, using long division. You got to get the same result. That's called synthetic division. Ladies and gentlemen, it really speeds things up immensely. Again, the only restriction is that your divisor has to be of the form of x minus c for synthetic division, to work. All right. That is the restriction. But this synthetic division you use quite a bit in college algebra, math 130 here at Mott, when you start trying to find zeros of a polynomial function. Ladies and gentlemen, I think I worn out my welcome here. In fact, I'm overdue by 3 minutes, and I do apologize. But hopefully you enjoyed the session. This has been recorded, and so you'll be able to watch this recording at your leisure if you missed anything.